the afternoon session, we have Ariel Yadin, and he will speak about intersectional IRSs. I forgot. Intersectional IRSs.
Okay. So what I'm going to discuss is joint work with Yair Altman, who is sitting somewhere here. And okay. So I'm going to try to present a new construction of IRSs. So I need to explain what these objects are and hopefully give you a construction, and I'll try to motivate it from a certain point of view, even though there are deeper motivations, which Yair brought this problem with motivations coming from more of his area of research. I kind of got interested because I was curious. So I probably won't mention anything about stack Zimmer or things like that. And if you want to know about it, then you can ask Yair later, and he will explain it to you. So, so I'm going to talk about entropy. So everybody, I was kind of sure everybody would have defined entropy in the previous talks, but I don't think it was defined. Maybe it was, but what I'm going to do is I'm going to look at the Shannon entropy of a random walk. So what I'm doing here is I'm taking some random walk on a group. So it's just a product of IID elements from some measure on the group. I'm going to look at the Shannon entropy of this, this distribution. This is the same thing as looking at the Shannon entropy of the teeth convolution. It's the same thing. I'm going to divide this by t, and I'm going to take a limit. Okay? And this limit I'm going to just call h of g mu. Okay? So this is the group, and this is the measure, which is underlying this random walk. And well, you can ask yourselves, does this limit even exist? Why can I take this limit? The answer is yes. This is actually not a difficult exercise. This sequence is subadditive, so you use, in the Hebrew University, you use Fekete's lemma to prove that this limit exists. And so, okay, but to prove that this limit exists, we used some property of this sequence, which is true for Cayley graphs, which is true for these kind of, so the title of the conference is Random Walks on Symmetric Objects. So you need some kind of symmetry, you need some kind, which is an undefined concept, for this sequence to converge. It's not true that this sequence will always converge for a sequence on for a random walk, say, on a general graph. Okay, so one question, for example, is, so here is a question, which I will not answer because I don't know the answer. So let's look at the set of all possible entropies where G is a group generated by D elements. Okay? And okay, maybe we want to restrict to, so let's say that this is just for simplicity, that mu has finite support and that it's symmetric. Okay? So you go over all possible entropies you can get from taking a finitely supported symmetric random walk on a group generated by D elements. Okay, for some fixed D. And you so describe this set. So for example, you can compute the entropy of the free group on D elements, right? And you can compute the entropy of ZD, for example, and you can try to compute other entropies. Sorry?
Are there any of these restrictions?
Well, maybe. So you want to say that you can get any number you want? Well, okay. But, oh, sorry?
There'll be some...
So, okay, so let me say what the obvious restriction is. So the obvious restriction is if you have a finitely generated group, it's a quotient of the free group. Okay? And you can easily, just by considering the finite time entropies, understand that if you have a quotient, the entropy can't go up.
Sure.
So this is always contained inside the interval 0, and you can get 0. I mean, that's basically every Liouville group is, every Liouville pair here is, it gives you 0 entropy. That's just the entropic criterion. And the maximal entropy is the entropy of the free group. So let me write it. FD simple random walk. Okay?
But your measure could be like
Yeah, so, okay, so. Sorry, what?
So you support it on the generated set.
Okay, so let's do. It's a vaguely defined question. Okay, yeah. What I'm trying to understand is what entropies you can get for you know, certain restriction groups. If you don't restrict anything, then of course you can just look at these free groups and kind of do crazy things. It's still interesting to say what entropies can you realize using random walks. I don't know how to answer this question. Okay, I don't know how to answer this question, but you see that because every finitely generated group with D generators is a quotient of the free group, this is a question about, actually a question about normal subgroups of the free group. It's about quotients of the free group. So you can rephrase the question. Instead of looking at this interval, I can look at, if I fix some measure, symmetric measure, and finitely supported maybe, on the free group, I can ask what values, so I can ask for the set of all I can ask for what the range of these values are, where what I mean by this is that I run over all normal subgroups of the free group, I look at the quotient, and I project a measure onto this quotient. So it's a different measure for every n, but then I run over all possible groups generated by the elements, and now since I fixed the mu in advance, this fixes the measure for all the quotients. And I can ask what's possible for this setting. So it's a question about normal subgroups of the free group, and basically, and actually what you're doing here is, if you think about it, this is a random walk on the cosets of this normal subgroup. So you're actually just looking at, you know, at finite time, you're actually looking at the entropy of the distribution of which coset am I in of this normal subgroup. Okay? So that's still open.
But coming back to the simple random walk question, do you see, do you know one number in that interval which does not appear? Is this clear?
Well, you have non-Liouville groups which are generated by the elements, which you can. I'm going to which have less than full entropy, but don't have zero entropy.
No, sir. Is there something you think that it's the whole interval, or is there some reason to believe that
There is some element which is.
Oh, you're asking what I believe? I don't know. It's a question.
No.
What is the conjecture? I think there are competing conjectures. I think that some people might say one way, some people might say the other way.
Okay, so
I don't know what to believe.
Is the following possibility completely wrong? It's the entire interval.
No. It could be the entire interval. It can't be more than the interval, but it could be the entire interval. A priori, it could be the entire interval. It's a question about, you know, kind of ubiquitous normal subgroups.
That's a one competing.
What?
given the knowledge of the world today,
Given my current knowledge, it could still be this interval. I don't know if anybody has found. Okay. That's exactly, I think, the point of this whole talk. So, if it was continuous, then I would be able to solve the question. Okay, it's semi-continuous. I will go to continuity. It's exactly what we use. Okay. So then I looked at this question for a second. Then, you know, so if you're a probabilist, you think, or if you think like me, then you think a normal subgroups is just one example of subgroups of a group. You can also think of groups that are not normal subgroups, but they're almost normal, or maybe they're normal on average. So, and this is where I come to this term IRS. Okay. Now, I need the normality to even have convergence of this entropy. So it's not true that if you just take a general subgroup n, then this thing will converge. It's just not true. So to even speak about a question like this, if I want to generalize from normal subgroups, to run over more than the normal subgroups, maybe all subgroups, then I need to define my question better because it's not defined just for general subgroups. So I'm enlarging the family of subgroups that I'm going to be able to talk about, and then I'm going to be able to actually answer the question. So it's an easier question. So what is an IRS? IRS means invariant random subgroup. And what it actually is, it's not an invariant subgroup. It's a measure on subgroups which is invariant to the group action. So groups act on their subgroups by conjugation. A group G acts on its subgroups by conjugation. And you can take a probability measure on subgroups which is invariant to this action. Okay. So I won't go into too much history about these objects, but what I will say is that if you have such an object, then you can define this limiting entropy. Okay? And again, you have some kind of stationary property that gives you the ability to define this limiting sequence. So what we're going to do is we're going to define the entropy. So, okay. So given an IRS, given IRS lambda. So again, this is a probability measure on subgroups of a fixed group G. Okay, so IRS lambda on G. And it's invariant to the conjugation operation. Then you can define H of lambda with respect to mu. So mu is again a measure of a random walk on G, on the original group. And you can define this just to be, well, I'm going to look at the entropy of the cosets of this random subgroup that I choose according to the distribution lambda. So it's, let me go down here. So I'm going to look at K is going to be my random subgroup. It's a randomly chosen. It's actually a function from the probability space to the subgroups, whatever. I'm going to look at its coset at time t. I'm going to take this quotient, and then I'm going to take the limit. Okay, and now you can ask the obvious question. So the entropy is just with respect to the random walk. Let me emphasize that. So the entropy is just with respect to the random walk, which means that this is a function of something random. So you fix a k, you get a number, but this means that this is a random variable. So you can ask, does this converge, and in what sense does it converge? So the easiest thing to do is just take the expectation, and I'm going to write it this way, just to make it clear, the entropy being on the random walk and the expectation being over the IRS. This is easy to see that it converges just from the fact that this measure is invariant, to group conjugation. This gives a subadditive sequence. Okay? So again, it converges. But in fact, you can use stronger theorems. They're not so complicated to prove, but you can use these Shannon theorems or Shannon-McMillan-Bryman theorems to show that, in fact, even without the expectation, this sequence converges almost surely. Okay, so there's no problem in defining things, but if you want, one definition is just taking the expectations, and then everything is subadditive and it's okay. So we have the notion of an...
Actually, it's better to refer to the Hillman theory, which is provide everything.
Yeah. But I think all of them can be reduced to some kind of subadditive argument. So basically...
No. When you do Shannon theory, you need to do some manual work.
Okay. I will not argue which method I think is simplest. If you work a bit with entropy, you get used to these things, and it's kind of immediate. But Vadim, I think maybe your opinion is you have more experience, so I will defer to it. Anyway, what I said is true. So this converges, and that's the idea I wanted to explain. And the next thing is that once I have a fixed group, a fixed random walk, and an IRS on it, I can ask, okay, if I vary all my IRSs, what are the possible entropies that I get? Okay, so say question 2, which I will answer, is maybe describe, or I will answer in some situations, describe the set H lambda mu, where lambda is IRS on G. So you have a fixed mu, a fixed G, and you vary all the IRSs. This, of course, is a bigger set than, so this set contains the previous, right? So this contains this set because, okay, let's understand why. Because a normal subgroup, if you take delta measure on it, if you take mass 1 on this normal subgroup, you get an example of an IRS. IRS is a generalization of a normal subgroup. Okay? Because, of course, if you choose n with probability 1 and it's a normal subgroup, then its conjugation is still n, then you have the same law. Okay.
Mu is still the simple random walk?
Mu is some fixed random walk, your favorite random walk. It's going to be symmetric, and at some point...
It's a simple random walk.
Okay.
And what is mu bar again?
So mu bar, when you take a quotient, you need to project this onto this quotient.
Okay.
It becomes maybe something else, but it's some laziness and, some... Okay. So, and again, the obvious, so this contains this set, but it's contained, obviously, still in the entropy of this full group. Just because, if you know exactly where you are with the random walk, then you know exactly which coset you're in. So this is very easy, just to prove an equality at a finite time level. Okay. So, and the obvious question is, okay, do you get the whole interval? Do you not get the whole interval? Maybe you get a small interval inside. What can you say about this set? We can talk about different properties. Okay? So, first of all, for example, if Gabor already mentioned the property T, so I don't know if this is a theorem or this is a consequence of some deeper facts. But kind of, if you looked at in Gabriel's talk about the definitions of property T, you can at least intuitively feel why it should be true, because there were some gaps coming into the definitions there, right? You had some things, you had some groups acting, and there were gaps in something there. So basically, I think that that behavior is, or the way I look at it is that behavior is leading to this consequence. It's a consequence. I think this follows directly from work by Amos Nevo, but maybe even follows from some other works. Okay, so but the consequence is that if the group has property T, then there exists epsilon, so that the interval 0 epsilon is not contained inside this set, which I want to give a name. Okay, so this interval I'll just call this set. It's not necessarily an interval, even though I use I lambda mu, and the intersection with I lambda mu is empty. So you could get 0 entropy, but...
Lambda should be in the intersection.
Sorry?
Lambda should not be in the I. Lambda is something that's set.
Yeah, what I meant to write is this. Yeah. Sorry, thank you. Okay, yes.
You must have said somewhere that you are considering a project matter.
Oh, that's a very good remark, and I didn't say it, but I was waiting for someone to say, okay, right. So the next thing is, yeah, okay. So somebody should have already objected to this, because it's a very simple argument to say that if you have two IRSs, and you just choose this one with probability P and this one with probability 1 minus P, you get an IRS, right? And you can check that the entropy with this kind of combination works continuously and nicely, and then what you have is you can realize the full interval between any two IRSs. You can do the full thing, you can do the zero thing, so you can get the whole interval. So what I mean is I don't want to take trivial constructions like this, so I want to take ergodic IRSs. Ergodic IRSs basically means that they are extreme points on the convex set of all IRSs. So since the set of all IRSs on G is the convex set, you can just look at the extreme points, and that's what you want, right? So actually what I want to do is write here ergodic. Okay, so it means it cannot be written as a non-trivial convex combination of other IRSs. Okay. So first of all, this shows you that this kind of studying this interval is a non-trivial, has non-trivial behavior. It's not that for all groups it's always the full interval or something like that. But for many reasons, actually, so very interesting case, which we are actually currently working on, and we can probably do most of the details, is to understand what happens in SLNZ, or maybe SLNR, which then I would need to define some other things. But of course, if n is at least 3, this has property T, so we know some things about this. In fact, we know a lot more. What I said here is just a consequence. You can really understand the IRSs on these higher rank lattices. But when n is equal to 2, so maybe right. When n is equal to 2, it's kind of still not understood. And here I would definitely conjecture, because we have most of the details already, that here you can get the full range of intervals, the full range of entropies, the whole entropy. Okay. But we didn't, this we haven't written down or published yet, so I'm just saying that formally it's still open. But so another motivation for what we did, aside from just trying to check groups and checking kind of the first groups that come along, is that the free group on 2 elements sits inside this group with finite index. So I say, okay, let me change the group a bit, and let's see something that maybe I can work with. But actually, I think historically, I mean, in practice, it didn't work out like that. I just said to Yair, let's look at the free group. Why look at complicated things? What happens there? He said, we don't know. We need to understand. They did know some things. But so this question about the free group was considered by others. So it seemed natural to continue with it. So here is the result. It shouldn't be surprising. Okay, so for any symmetric and finitely supported mu on FD, on the free group on D elements, this interval is just the full range of possibilities. So the maximal one, this is the minimal one, and you get everything. Okay? So you say that this has full realization. Okay? Now, let me just make 2 comments about this theorem. So this was first considered by Lewis Bowen for the case where mu is the simple random walk on these generators and their inverses. So just basically looking at the deregular or the 2 deregular tree and considering that. And he has a beautiful construction of IRSs that give you full realization for that specific neighbor. But his construction inherently cannot walk if you change kind of the tree structure. The tree, it relies heavily on the fact that there is a tree going on in there, and it's not a random walk which can kind of do weird things on the free group. So that's one comment. So this generalizes Lewis's result because, and another motivation to generalize this result is because we want to go from here to here, and when you work with these things, finite index always kind of leads you to non-finitely supported measures. And I have to be frank, I think we did finite support because I was a bit lazy. There were some random walk lemmas, and I said, okay, let's do finite support, and then I said, okay, let's just, Yair was in America already, and you know. So. But we're working on the infinite support, so at least with some nice tails, and that shouldn't be, I mean, there's nothing really deeply different about that. It's more a technical random walk analysis than anything else.
Can't you do it directly
For
for free products?
free products?
Well, self-assessment free products.
I don't know how to do it directly. I mean, I will show why the free group is. I will hopefully will get to something about the construction. But so now I want to give you first a general construction of how you construct IRSs, and then show you how you do it in practice for the free group to get the full interval. Okay. So. And I mean, to our knowledge, this construction of IRSs was kind of new. Basically, what people do usually to construct IRSs, and in fact, it's what you always do when you construct an IRS, because a theorem by, I have to get the order correct. So it's Abert, Glasner, Virag. So a theorem by these three authors is that any IRS comes from looking at some space that the group acts on, taking stabilizers of points. You have an invariant probability measure. The stabilizers will give you all such stabilizers will give you IRSs. So you're always constructing a space, a probability space, which the group is acting on, and just looking at stabilizers. But that's not how we construct it in practice. We are going to give a different actual construction, which is kind of a different perspective on how we do things, and it's very different from Lewis Bowen's construction, and things kind of work in a certain sense, which I don't know if I will get to explain, in opposite directions. So somehow in the free group, Lewis is going from the right side of the interval down to 0 in a sequence, and we are going from 0 up to the right side of the interval. So the construction, I think, is inherently different, and that's why we were able to do much more general random walks than just the simple random walk. Okay, so what is the construction? So the construction is the following. I'll give a special case of it. So let's look at the following setting. So we have some group G. Okay, we have a random walk on it, which we can remember later for entropies, but now I'm just constructing IRSs. So IRSs don't care about the random walk, right? They just care about the group action. So you can forget the random walk for a minute. And we have this group, and suppose we have a subgroup, okay, which is now not a random subgroup, just some fixed subgroup, and specifically it's not normal. It's not necessarily normal. I mean, if it is, things will just become trivial here. Okay, so what we can do is we can look at the orbit of this subgroup under the G action. Okay, so we can look at all. So this is the orbit of K, right? It's all the elements of G acting on K. So by this notation, I just mean this conjugation. So it's a right action. Okay, so we look at all conjugations of my subgroup, right? And the group acts on this because it's an orbit, right? So it just permutes these things. And so suppose we have some measure on this thing. For example, let's just look at the counting measure. We don't really need to do the most general case. Okay? So we're counting how many objects there are in terms of, so many of these identify, right? So there could be much less than the number of elements in the group. I mean, much less. They're both probably infinite and countable, but some of these different conjugations can be the same. Okay? But suppose you put the counting measure on this set, and what you want to do is you want to define a norm for elements in the group. Okay? So I'm going to define this to be, so it's going to, okay, so I use the counting measure, right? So it's going to be the number of conjugations k to the gamma, counting them as different sets, okay, such that this is not a fixed point of this specific element, okay, such that so I take the complement of the set, so let me maybe make it, so I have some measure m on my set on which the group acts, and I'm actually looking at the complement of the set of fixed points of the element G. So if you want to think of it in a more abstract way. But as for a concrete example, we have this. Sorry? M is just the counting measure, but you can think of a general thing, a general orbit, a general measure on the orbit, and you just take the complement of fixed points and measure it with your favorite measure. Maybe it's different than Ori's favorite. Okay, but that's exactly what's written here in the case where you take counting measure and on this. Okay. So what are the properties of this? So it's very easy to see.
Unless the normalizer of k is a finite index.
If the normalizer of k is a finite index, it's actually nothing is really going on. But so what's the question?
Is it this infinity?
Some cases it's going to be infinity. Some cases it's not going to be infinity. Yeah. So this is valued in 0, infinity, including infinity. Yes. Could be 0, could be infinity. Don't be confused because I used the two lines to depict the norm. There are going to be some norm-like properties, but it's not a norm in the usual sense. Okay. So, I mean, it's also I'm defining it on an abstract. But anyway, the three properties that I want to see, so this is quite easy to check just by definition. So one, the norm of two elements is just, the product of two elements is just at most their sum. Okay? I think, is this okay? Can you understand? I'll try to cram it. Okay. Right? And 2 is that the inverse has the same norm as the original element. And 3 is that conjugating by anything doesn't change the norm. And in fact, I was surprised to learn that these have been used in other contexts completely independently of our work, and people have been studying such objects for different reasons. Okay? So what do you do with this? Well, first of all, you notice that this gives you a subgroup structure, and this gives you a normal subgroup structure. So you can define two normal subgroups with respect to such a norm. One normal subgroup, which let's denote by K0, is going to be the set of all G that have norm 0. And just these three properties tell you that this is a normal subgroup. Okay? And another normal subgroup, which is denoted K star, is just a set of all G that have finite norm, including norm 0. And this is another normal subgroup. And you see that K0 is a normal subgroup of K star. Okay? Okay, so what can I do with these things? Well, here is a theorem. So G mu, as before, K is a subgroup of G, and assume the following. So we're going to assume, so I have normal subgroups, so I can consider their quotients under G. So we're going to assume that the bigger one, so this is the bigger one, remember? So we're going to assume that the bigger one is almost all of G. In what sense? Well, with respect to this measure mu, I'm going to assume that the entropy of the projected random walk is 0, which is another way to say that this quotient is a Liouville group with respect to this measure. Okay, so K star, in this sense, K star is almost all of G. Okay? Then, so these are all assumptions. Then, the interval of entropies contains 0, which is actually this, up to the entropy of the quotient with K0. So you can interpolate with ergodic IRSs in between the quotients of these two normal subgroups. Okay? Sorry? Yes, and I'm going to say something about that right now. Okay? So if K0 is, so if I can, so for example, if I can show that K star is the whole group, right? And K0 is just a trivial group, then I'm done. Okay? Did I get confused? I didn't get confused. I did the inclusions in the right one. Okay. Sorry? Again?
Okay. He says you didn't say that.
Like if K star is everything and K0 is trivial,
Then you are done.
Yeah. Now I want you to notice a few things. First of all, if the normalizer was finite index, it meant I had only finitely many conjugations. Then actually what's going to happen is that K star and K0 are going to be identified. And then what's going to happen is that even if this condition holds, I'm not really going to get any information. Okay? So we're only talking actually about infinite index subgroups. That's one thing. We want an infinite conjugation class. In fact, it's very important that this conjugation class is infinite for these IRSs to be ergodic. I'm going to show you what the IRSs are, why they are called intersectional IRSs. Okay? So I'm just going to define what these IRSs are. Okay? So, proof. Well, I have to build an ergodic IRS, right, to get any value in between these two things. Okay? So, for, how should I do it? Okay, so let's do, so we've seen percolation today, right? So for P in 0, 1, and the generalization to general measures instead of the counting measure, which I did before, is just by taking Poisson processes. But for P in 0, 1, I'm going to let omega P just be Bernoulli percolation so it's going to be a subset of this conjugation class, right? Which I'm now assuming is infinite, otherwise the whole theorem doesn't give any information. And so I'm just choosing every single element in this set with probability P and discarding it with probability 1 minus P, and this is my random set. And then I'm going to define, say, no, it shouldn't be this because it's not going to go in the right direction. Well, okay. I will define K1 minus P to be, so by definition, it's going to be a random subgroup, and it's just going to be the intersection over all elements inside this random set omega P of this conjugation class. And you can see that the action of G on these conjugates becomes an action on subsets of this set, and this is Poisson point process, so it's invariant to the group action. Moreover, we can understand the limits of this in the correct subgroup topology. So this is a random subgroup, and it's an IRS. Okay? And it's an ergodic IRS as soon as this thing is infinite. When it's finite, it's not ergodic, but again, when it's finite, the theorem doesn't do anything. Okay? So it's always going to be ergodic. Just think of choosing Bernoulli percolation in an infinite set. That's an ergodic subset of under all possible group actions. Okay, so this thing is ergodic, and what happens when P goes to 1 and when P goes to 0? What happens to this in the appropriate topology on subgroups, which I don't want to go into because I'm almost out of time? Well, this converges, as you can probably guess, and if I didn't make a mistake in the notation. So let's see. When P goes to 1, right, I'm basically intersecting all of the elements, right? So the only guys who I cannot catch are the guys who have, so the only guys that I can't kind of throw away are the guys that have 0, yeah, so, okay, so I will write another line, and then it will explain these two better, but the line is just that the probability under this choice of omega p, so it's a probability p, the G is in K1 minus P. So what does this mean? It means that I have to be in every single one of these guys, right? So it means that basically it means that the fixed points of G cannot intersect. Sorry, it means that the fixed points of G must contain omega p. Okay? So what this means is that omega, now it's 1 minus p, right, must be contained in the fixed points of G. Okay? So basically what it means is that my process has to miss the complement of this set, right? So it means that I actually have, so this is, so I miss it with probability p, right? And the number of elements in the complement set is just the norm of G. Okay? So this is 1 if this is 0, always. It's 0 if this is infinite, always. And for the guys that have values in between, this converges to the appropriate value when you go to 1 and to 0. Okay? So it's actually very simple construction. I mean, the proof, once I give it to you, it's an exercise. Oh, so that's the question. And you should notice that I had this condition, this bothersome condition. Why didn't I just say, the entropy between this entropy and this entropy, all values can be realized by ergodic IRSs? And that's exactly the problem that you have. You cannot do, well, we don't know how to get information about, we have these nice ergodic IRSs. So in fact, without saying anything about entropy, I have just a bunch of ergodic IRSs. For different P's, they're mutually disjoint. They're mutually singular. They're living on different spaces because the percolations aren't living on the same spaces. And so you get uncountably many different ergodic IRSs when you have this situation. But to say something about entropies, you already need some more information. And the fact is that entropy is not continuous. So if you define so let me write caveat. If you define this function h of p to be just the entropy of so I need a measure. Okay, let's just write G modulo this k 1 minus p nu bar, right? So if I look at the entropy of the IRS, okay, then this function is not continuous in P. But using basically standard results about functions, which we also discussed at lunch. But basically, you have some half continuity when you deal with entropy and the correct convergence. This is why it was important for us to understand what the limits here are. What you will have is that this thing is going to hold. So you have this kind of inequality. So h of 0, what is h of 0? This is when you do, this is going to 1, right? So you get k0, right? So that's the one I wanted to be. Did I do it wrong? No. Yeah, so this should be p. So let's see. When p is going to 0 here, it translates to 1 minus p. So this group is going to the k star, which we said is basically the whole group. It's basically and has 0 entropy. So that's very good because it's going to give me information about these. It's going to say that the limit is actually 0. Okay? But if this was positive entropy, I just don't know anything. I really don't know anything. I don't have any other method of bounding the entropy of these things. But once you have 0 entropy, you get this, interval of entropies. Okay, so it's all because of this semi-continuity. Now, so for example, if I had a bit more time, I would show you the construction immediately for the Lamplighter group. If you take a very general type of Lamplighter groups, you can just construct K so that this becomes the commutator of the group, and this is trivial, and then you have this, and of course the quotient with the commutator is an abelian group which has 0 entropy no matter what measure you take, so you get a full realization for Lamplighter for just by writing down one subgroup. Okay? But, so then the next step was I said to, I said to Yair, okay, so let's do the free group. We have to work hard and guess the correct subgroup, compute k star and k0, and get full realization for that, and then we are done. One-line proof of Lewis's result. And of course, we couldn't do it. Well, we didn't manage to do it, and then Yair told me, oh, you can't do it. Why can't you do it? Well, because, which one is, I keep confusing the notation. So this thing, this quotient, remember, that's a normal subgroup of that one, and you can take the quotient and you can look at it. Well, this is embedded in finitely supported permutations on some set. If you think about it, that's exactly what's going on here. So this thing is amenable. Okay? And what are the assumptions of the theorem? The assumptions of the theorem are that you have these guys, and that this thing is Liouville, right? Which, for some measure, which just means that it's also amenable, right? So this would mean if you had the situation where this was trivial and this was almost the whole group in the sense of being Liouville or being co-amenable, then your group would be amenable. So you can only do that maybe if you have an amenable group. But you can't do it if you have a non-amenable group, like in the case of the free group. So for the free group, we had to make a better construction. And just one sentence about this construction. So what we do for the free group is that we find the sequence of subgroups Kn, which is going to be very bad notation because of this. Well, okay, I will keep it. So we find the sequence of subgroups for every n, okay, such that this thing, so for each one there is a star group, okay, this thing is going to be just nilpotent. Basically, this is going to be some third commutator or something. It's not really important. It could be just a commutator subgroup when d is at least 3. When d is 2, you have to be a bit more clever. So then it's Liouville for any measure. And Yair proved it this week, actually, for anybody who was at the talk. Okay. But the other side is that I need the entropies of the other quotient to go to the full entropy. So the other condition is that the entropy of this Kn0 with the projected measure converges as n goes to infinity. So you have a sequence of numbers. You can interpolate between 0 and these numbers for every n. And these numbers converge to the full entropy of the free group. That's how you prove the full realization theorem. The way to construct, now the very interesting thing about this construction is that it's not very difficult for me to describe this fixed subgroup. I can describe its Schreier graph, actually, and then you can try to see what the subgroup is. But computing the K0 and the Kn0 is actually, which is actually the normal core of this subgroup, is actually not a easy, well, we don't find it very easy, I think. In fact, even in much simpler cases. And we had this clever trick of bounding this entropy below by something we can understand about the original subgroup, which, again, doesn't have to have a limiting entropy, okay, because it's just a regular subgroup. It's not necessarily normal. We bound this below by some quantity which we can push to the full entropy. So we really don't know these numbers. We really don't understand how these things grow, even though I can give you a very, very simple description of the Schreier graph of this group. Describing the normal core of a group given its Schreier graph, I don't know. This is even in, we are now trying to think of simpler cases and we can't do them. So maybe we will be able to in the future, but at the moment it's a bit mysterious. So these subgroups are kind of mysterious. Okay, and basically this is the only step. This is the only step where we use the finite support of the measure. So we need symmetric measures, but using the finite support is only in this step, and it's definitely generalizable to a wider class of measures, which will then be the first step to going to SL2Z. Okay, so that's it.
The first question. So you've been talking about random subgroup, but there is an equivalent description in terms of the graph.
Yeah.
Can your construction be maybe recast or explained in terms of diagrams?
Well, you mean how to construct these? We construct them using Schreier graphs.
No. You are constructing a certain invariant measure on the spatial subgroup. This is the same as to construct a certain invariant, or as some people prefer to call it, the modular measure on space of random track.
Yeah, so you mean,
Can
okay.
you describe it in terms of graph?
Well, you see, if I draw the Schreier graph of this guy, right, then what I'm doing to get the IRS is just intersecting each conjugacy class, each conjugate of it, independently. So what I do is I just color the vertices of my Schreier graph and look at the Schreier graph rooted in those and intersect what I get from each one of those. So I can just walk on the Schreier graph starting from only the red vertices, and things that close loops in all of the red vertices will give me my the elements of my random subgroup.
No, I know how one gets random subgroup from track graph. My question was about track graph.
But okay, so I'm saying even a very concrete question. Okay, let me pose a question. Maybe you will say, oh, I know the answer immediately, but this is a question I don't know the answer to. Okay, so even a much simpler Schreier graph than what we had here, this will not work for our purposes, but or probably not. But suppose I tell you, okay, K is the subgroup which has Schreier graph which looks like this. It's basically a copy of Z2, okay? And you just, here, you add a vertex and you put a self loop. Okay, so this is a Schreier graph of the free group on two elements. It has a subgroup K. Now, draw the Cayley graph or the Schreier graph of the normal core of this guy. This is the normal core of K, right? It's the intersection of all conjugates. So draw the Schreier graph for the. I think I can prove that it has girth at least 6 or something like that, or maybe 12. I don't remember exactly the number that comes out, the smallest loop that you can close. But this is just the Cayley graph of the quotient. It's mysterious.
I understand, because you want the action to be
I didn't hear you. Sorry.
you want the action to be non-trivial, so that's why you kept it at the bottom.
Yes. Yes. Yeah. No.
Maybe I can answer your question. So imagine
okay.
that the group, instead of the free group, it's, let's say, a free product of Z2s. And imagine that you take an amenable group, nice finite integer amenable group which has drift, so which has positive entropy. And then now color the edges of the Cayley graph now with this, let's say, 5 colors. And then you have now an action on this thing. So you get the Schreier graph of this very non-amenable group. But of course the graph itself is very amenable. And of course what you can do, and you know the IRS now because it's amenable, so you can average out, and you know just this classical Bogoliubov construction, and then so you got an IRS. And then I just wondered when I listened to this thing that if you just take edge percolation with this sort of thing, then you've got like a kind of like a scaled sequence of IRSs. Isn't it true that if you do that way, then the entropy will be actually continuous, and up to the the critical point, maybe?
Why should it be continuous? It will still be an infimum of continuous functions. But the infimum of continuous functions is not necessarily good. I think it might be true, and I think that's what you need to prove. I think
it's so hard to imagine that if you take really percolations, it's less and less edges than somehow.
So even monotonicity is not known. The monotonicity of entropy is not known. So if you have more edges, is entropy higher?
And if you knew that it was one thing, you know that the local property is invariant time the change of time generated.
I see.
I don't think there is a simple
You got
solution.
So you can get the IRSs, but you do not
Yeah.
know that.
So there's a difference between getting many IRSs, even mutually singular IRSs, ergodic and everything, then still getting entropy. You see, if I did this on lamplighter on Z is Liouville. I would get uncountably many mutually singular IRSs. All of them will have entropy 0. So there's one thing to construct the IRSs, and there is another thing to analyze the entropy.
There, as we know, there are two definitions of the entropy, either in terms of the evolution or in terms of the boundary action. So in your case, can you interpret these intermediate entities in terms of, do you see the boundaries of these random processes in random environment?
Very specifically for our construction for the free group, okay, so I think of it differently as a probabilist, and I think of the entropy as, as the random walk, and I look at it this way. But very concretely, for this specific construction, I can probably, if I worked hard enough, describe the full boundary of these different IRSs, and you'll see that it's just approximating the counter set. But probably using your criterion, you can do it maybe even completely rigorously. But I prefer the. It was already quite long, this paper, but this was much easier to do, and we didn't give a full description of. No, we just showed it contained some information which was enough to push it.